This will be the lecture over chapter 15, and we will be just looking at brachytherapy and what are the advantages and disadvantages of brachytherapy. We'll be looking at several of these attributes as we go along. We'll have some nice little postage stamps here from different countries illustrating how those that developed brachytherapy, how they're memorialized today and in years past. We've got histories here. Now, if you take a look here at Alexandra Danlaus, in 1901, he was actually using different types of radium salts in order to treat lupus. He was a physician that was experimenting with the use of brachytherapy and what it could do against diseases in the human body. And a lot of that was done using radium salts. Now, the problem, at least back then, with radium salts is the fact that the material wasn't a lot of it. And you had to be careful how you handled these things because it, under the right conditions, if you had a crystal lattice, the alpha decays would actually weaken the lattice, and you could get explosions, which, in an operating room is not exactly what we're looking for. So one way to try to deal with trying to control some of the reactions that you have out of radium, some of the decays or whatnot, you want to filter out some of the lower energies and maybe just get those that are penetrating to do what you need them to do. And that's where the idea of the Dominici tube comes from, which you can look at it here. This is the idea of saying, hey, maybe if I take some of this material and encapsulate it and perhaps shield it using silver, lead, some other type of metal, you can filter out some of the things that you don't want and keep the stuff that you do. And therefore you could put it next to whatever it is you're attempting to treat in order to be able to treat the disease. So, and even after, this is what you're looking at early on when you don't really have a lot of data to deal with. After 1950, you're looking at different types of radioisotopes that you might be able to use in place of radium, which again, looking at around 1914, 1920, you're looking at something that was even more expensive than gold if you look at it in terms of a per unit amount. Not only do you want isotopes that are going to be a little bit more useful, you're also looking for ways to be able to load it into the patient without exposing the practitioners to undue or excessive amounts of radiation, which is something you obviously don't want repeatedly. And so you're looking at specific after loading devices to be able to do that. So you have a long list here of events in which the application of brachytherapy was occurring. So what is brachytherapy? What do you use it for? Why would you want to use it? And the different types of applications, interstitial, usually that's going to be handled by a physicist. Intracavitary, you might have therapists involved as far as taking care of the patient, setting things up at the direction of the physician or physicist. You might have intraluminal, intravascular, topical. It kind of depends from place to place exactly how much a therapist may be involved with these kinds of things. So in radiotherapy, it's the source of a radiation is placed close to the surface of the body or within a body cavity. In other words, you're going to want to put, rather than in teletherapy, where you're going to be zapping it from a distance, The brachytherapy, you're actually taking the radiation and you're putting it within the tumor or very, very close to it in order to be able to have the rays release and interact with that tumor. It's just sometimes it's just easier not to have to cut through so much normal tissue in order to be able to get to the problem. Obviously, brachios is the same as short, so that's where brachytherapy comes from. Again, this is our discussion where a source can be placed in or near the cavity. Source strength specification. So you've got 3 roles in brachytherapy. You set the standard for describing quantities. You help form the basis of computational dosimetry, and you serve as a prescription parameter. In other words, this is factored into how much exposure do you want to prescribe to the patient. It's measured in curies. It describes activity, number of disintegrations per unit time. And this is still used, although in many cases you may be looking at millicuries or some subunit of the curie. You're seeing here where the number of decays with respect to time is going to be proportional to the number that you have. The activity is going to be the rate of decay of radioactive material or change in the number of atoms over a given time. Is directly proportional to the decay constant. So as the decay constant increases, so does the activity. The half-life, it is the time taken to decay to half its original value. It's related to the decay constant in this fashion. This was actually the natural log of 2 here. So the half-life is going to be the natural log of 2 divided by lambda. It is inversely proportional to the activity. So as the half-life increases, the activity increases. The radioactive decay, the decay formula is here. It's something that is very similar to the number that we have present is equal to the number that the number present is equal to the number we started with times a factor of this power. This will predict the decay. So if you know what the unit is producing at some particular time, if you know the amount of time that has passed, you can determine the activity later on. So the mean life, the average lifetime for decay of radioactive atoms is what this is referring to. It's applicable to permanent implants and gold 198, iodine 125. And this is how it's related to the half-life. So basically you take the half-life, multiply it by 1.44, and you get the average life. So the average energy is denoted as E sub average, and it's derived from the decay schemes of each one of these isotopes. So you have the isotopes listed here, and then you have the half-lives that are associated with that. Sealed sources, such as what we have here, you've got radioactive material inside, and the ends are welded shut, so they don't escape. And it is there to prevent the absorption of beta particles. So you've got, when it comes to radioactive sources, you have an active length, which is the length of the area in which the radioactivity lies. You have filtration, which is the thickness of the source capsule, basically how thick is it to block certain types of radiation getting out. And then you have a gamma factor. So for radium-226, the gamma factor is going to be 8.25 Rankins centimeter cubed divided by the millicuries times the hour. This assumes a filtration of 0.5 millimeter of platinum. For radioactive sources, the radioactivity is expressed in milligrams of radium. We are assuming 1 milligram of radium has an activity of 1 millicurie. A full strength source is 0.66 milligrams per centimeter of activity. A half strength source is going to be, of course, half that. This is a decay of uranium-238. This is the chain as it goes along. So eventually the uranium ends up at lead. But in the process, as you go through, you can see radium here as a link in that particular chain. You can see the alpha decay and turns it into radon gas. This will exist around for 1600 years. We've got multiple energies here. We have with the alpha, you can see the energies listed here, and then we have gamma that goes along with that. You can see the most probable energy that's being released listed here, followed by this, and then followed by that. Now, how are these sources loaded into these particular types of needles? Well, you've got a uniform distribution here. You've got what is called an Indian club. We have a full strength here, and then you have something a little bit more here towards the pointy end. You have something called a dumbbell, where you have a smaller amount that is inserted here with heavier amounts there at the ends. And then, of course, you have a tube here where you have, rather than just a pointy end, you have rounded ends at both spots. Needle sources, you still have safety problems. They're stiff, therefore you have a chance for breakage. And you have high personnel exposure. For tube sources, they are rounded at each end and they contain a larger amount of activity, and they are developed for afterloading. Permanent tube sources, you have radon and gold, which have very short half-lives. You saw, if you were looking up there earlier, it's close to 4 days there, I think. Packaged in seeds that are 3 to 5 millimeters long, and they're common in prostate implants. Radium substitutes, because everybody enjoys working with radium, right? And there's no better way to deliver brachytherapy than through radium. So the dosimetry is based on the original radium work. I mean, you do a lot of work with radium, so you know a lot about it. So you can try to relate back to that. Some examples here are cesium-137, iridium-192, gold-198, iodine-125, and of course the activities are expressed in millicuries. If you want radium equivalents, then the milligrams of radium equivalent, you've got the activity of the isotope in millicuries, and then you take the gamma constants for each one, and you develop a ratio between them, and then you can produce this particular value. So if you have a 25 millicurie source of cesium-137 and you want to find the radium equivalent, then you find the gamma for that cesium-137 divided by the one for radium, and then you can produce that. So cesium-137, it is, well, at least at one time, was widely used. It replaced radium for the uterus and cervix. Here's her photon energy for that, and it's comparable with radium, you know, within very close to the same energy. The advantages, the lower energy, so you have fewer safety hazards, and then you have a half-life of 30 years, so the sources can be used for quite a long time. You can see that it beta decays into barium-137 and a metastable, and then barium-137. You can see the half-life there of a little over 30 years. You can see the energy. So most of the time it's going to head here and then head here, but you do have instances where you see a beta decay about 6.5% of the time straight to this value. And then you've got cesium-131. Decays by electron capture into xenon. Average energy of 30 keV, so it's much smaller than what we saw before, and a half-life of almost 10 days. You've got iridium 192. It comes in a wire form, which you can see sort of bent here. Also undergoes beta decay. Average photon energy is about 370 keV. It's got a half-life of 73.83 days, and it's used for the more temporary implants in a breast or tongue. Ugh, that looks fun, doesn't it? Other radium substitutes, you're looking at cobalt-60. Not really used that commonly for brachytherapy. It does undergo a two-tiered beta decay. You have two different energies that if you take the average is going to be about 1.25. The half-life is about 5.25 years. Normally, this has been used as an external beam source, but has been replaced with your more modern linear accelerators that just have more of an ability to penetrate than what the cobalt does. Gold 198, it's used for permanent implants and HDR therapy, primarily here for the prostate. Has a very short half-life of 2.7 days. Your energy here is monoenergetic, so you got one. Low energy, and there's low radiation risk, but it does what you need it to do. And again, you can kind of see the decay scheme here. Iodine 125 is going to be used for the LDR, interstitial implants. Decays by electron capture, has a very low energy compared to what you've seen before, has a half-life of almost 60 days, and there's minimal shielding that's needed for this. I mean, I didn't know that titanium could be cut that thinly, but apparently it can. So you've got photon emitting sources. You've got palladium 103. It's got a half-life of 17 days. It will decay by electron capture to rhodium 103. Average energy of 21 keV. Strontium 90, which has a half-life of 29 years. Beta decays into yttrium 90 and has an average energy of 0.93 MeV. And you can see the deposition density, a lot of it out there in Nevada and next to it, Utah, Colorado, those mountainous states. Beta emitting sources, yttrium 90, it's a result of strontium 90, which we just discussed. Has a half-life of 64.2 hours or 2.67 days. And here's its average energy. You've got californium 252. It's not a pure neutron emitting source. You have alpha decay most of the time, a little bit of fission. Half-life of 2.6 years. Average neutron energy is this. Average photon energy is this. Exposure rates. It's calculated using the following equation. So your exposure rate, you have your isotope, gamma, and then you multiply that by the source activity. And then look at that, distance from the source to point of calculation. Your inverse square law is coming back into play here. So you make all of that multiplication together there, boom, you get your exposure rate. High dose rate, HDR, brachytherapy. Most of you will probably have very little to do in this particular realm. If you do, most likely it will be taking the patient to get them CT'd for planning, which is mostly how things are done. It used to be such that they would, oh God, in the wars old days, when you would take x-ray films of the poor patients that are trying to have brachytherapy delivered, especially in the lung. Oh boy, that was rough. Where you try to take orthogonal, most times semi-orthogonal films, and try to be able to locate the source and plan off of that. That was a nightmare. Most of you guys are going to end up going through and doing CT so we can do CT planning on these systems, which is far better for everybody involved. It's delivered on an outpatient basis. So they show up that day, they get it done, and then they leave. The treatment time really isn't that long. And it's used for not only head and neck, but also gynecologic, breast, as well as prostate, and can be just as effective as LDR. So you got a device here that's going to be placed in the treatment area. It's connected to the brachytherapy machine. You've got a single small source loaded into it. You've got a high dose given over a short treatment time, and the time depends on the source intensity. So the more intense it is, the less time that it has to dwell there. And usually when you end up doing decays on these particular plans, the topology of what it is that you're treating generally doesn't change, so you can decay the plan. So the time is going to be a little bit longer for each subsequent treatment. The advantages here is that it's more convenient than LDR. LDR is going to be more of your inpatient treatment. And outpatient is going to be more of what you see with the HDR. Shorter treatment time, you're going to have, a matter of minutes, discounting everything you have to do to get things set up, versus days in the hospital. And it's that you don't have a hospital stay, you can make a lot of insurance carriers happy because you're not there having to be monitored. Brachytherapy application methods. You've got an external or mold that can be done, interstitial, intracavitary, endovascular, intravascular, if you're into that kind of thing. External applicators or molds. These are going to be used for surface lesions. They're designed to fit to any particular shape. An external application eye plaque, iodine 125 to treat uveal melanoma. Interstitial applicator sources placed into or adjacent to tumors, can be permanent or temporary. Permanent implants used to treat inaccessible tumors. So palladium 103, gold 198 have short half-lives. Iodine 125 is ideal for deep-seated lesions. Gun type applicators with long insertion needle can be used. So if you've got a colorectal implant, you can kind of see sort of what's going on here in this particular. Boy, that looks like a mess. Glad I'm not involved with that. Applicators and instruments, temporary implants, they are removable. These are for areas with no body cavity or orifice. Source placed directly into the tumor or the bed or in the uranium 192 after loading is in fact common. Applicators and instruments, after loading, hollow needles inserted into the tissue. Needles accommodate catheters with isotopes. The catheters are placed in the tubes before the removal, and the steel tubes are removed. Dummy sources are placed in the catheter for non-radioactive radio-opaque seeds. After loading, so the dummy sources aligned like the radioactive seeds, so that you can sort of practice what's happening there. They ensure proper implant positioning. You want to make sure you hit your spot. Following planning, dummy sources are replaced with radioactive sources. Stabilizers and guides. It improves accuracy of needle placement. You want to be able to make sure you hit your mark. So if you need a stabilizer or some sort of guide in order to be able to get it in there, that will help to make sure you're hitting what you want to hit. The different type of instruments that you have here, you've got tandem and ovoid. Tandem and ring is also can be used. That's what we used at OU to plan several different treatments. For a tandem and ovoid, the tandem is a long, narrow tube that's inserted into the cervix. The ovoids are inserted into lateral fornices of the vagina. It's much like this. There are certain points that certainly when you planned on film, that you wanted to take note of. Point A was 2 cm superior and 2 cm lateral to the cervical os. So you got your os here, so you're up 2 over 2. This is supposed to be where the uterine artery crosses one of the ureters. Point B is going to be 1 cm lateral to the medial aspect of the pelvic sidewall, which is very hard to see here. Usually, a lot of times you would use the guide that it would be 3 centimeters over from A. This is to represent nodal chains like the obturator node. Good luck anatomically if it actually matches up with that, but that's the theory. Vaginal cylinders, customized to avoid the bladder and the rectum, and it's a high dose to vaginal lesions and can be used with interstitial implants. The cylinders were usually a lot easier than the Tenement ovoids, usually a lot quicker to plan because you don't have to worry so much about not only the ring, but also you don't have to worry so much about the ring of the ovoids in addition to the tandem. Intravascular stent applications. This is an alternative to a coronary artery bypass, and of course you wouldn't want that. They inhibit arterial restenosis. Can be used with catheter-based systems, can be used with radioactive stents, and iridium-192 is what's common with these. Now, the basis for how these radioactive sources work, you've got dose distributions from radium-226, and you've had 3 systems here that were developed in order to be able to distribute or calculate what that dose is going to be. Patterson-Parker, you've got the Quimby or Memorial system is another way, and then the Paris system. So Patterson-Parker, also referred to as the Manchester system, as if you needed something else to remember. This provides a dose of plus or minus 10% within the implanted area. So you're achieving some sort of homogeny in the distribution. It's a non-uniform distribution of radioactive material. If you want the dose to be within plus or minus 10%, you're going to have to compensate in certain areas and not have it as strong in others. And this is supposed to provide a uniform dose distribution. It assumes the use of linear sources. The rules are established for planar and volume implants, and they are indeed complex. The Quimby or the Memorial system differs in that the activity is distributed uniformly as opposed to non-uniformly here. And it's used less often than the Patterson-Parker system. The Paris system, very similar to the Quimby or not the Manchester, but the Memorial system. It has a uniform distribution, unlike what you're seeing here. It's based on 3 principles. You've got radioactive sources must be rectilinear, which is linear in shape. Activity must be uniform along each source, and the sources must be spaced uniformly. It's used with long line implants or iridium-192 wires. Computers are now going to be doing a lot of the calculations for these things, which trust me is better in many aspects. The Sievert integral, it breaks the linear source into tiny components, calculates dose at every point, and adds values to get the result. And most implant procedures are going to be using computers, and you can check the dose with the Patterson-Parker tables. So we're using brachytherapy. Brachytherapy is often used in order to be able to treat certain diseases, but what are the ways that we protect ourselves as practitioners and also to protect the patients? This information is going to be regulated by the NRC, which takes care of the licensing, radiation safety training, personnel monitoring, all of that fun stuff. Okay, so storage. Eating, drinking, smoking, application of cosmetics are considered prohibited. Cannot be stored with food, drink, or personal items. Not exactly sure why anybody would want to do that. Must be secure and clearly marked. Obviously, you don't want to have a surprise if you're opening up something that you didn't know contained those kinds of items. Usually you're going to be working with a hot lab where the equipment is a survey meter, a well counter, safe, storage for spent sources. The requirements are that it's ventilated, lockable. You've got warning signs saying, hey, this is a hot lab. You probably really don't want to wander in here, and they are adequately shielded. You have a sink with a filter or trap. It is provided for cleaning source applicators. The last thing you want to do is to have a seed or part of a link that ends up getting lost, because that can lead to some real accountability issues. So when it comes to the inventory, when did you get it? How long has it been there? The number of activity of the sources removed, number of activity of sources remaining. What did you use? What's left? Who did you put it into? Where is it going? And who's responsible for receiving, or for that matter, sending? Usually to prepare these kinds of things, you need to carry it out behind a suitable barrier to shield the operator. If you're trying to load an applicator, that can be difficult. The last thing you want to do is to put your eye up real close to make sure that it's going in the way you want it to, or for that matter, getting your hands anywhere as close to those things as possible. Those are the kinds of things you want to avoid. So you have an L block. If you guys ever end up seeing something like this, I doubt you'll ever work with it. But the L block here allows you for being able to see what's going on there, but also shielding you from what's going on in the source itself. And the long forceps should be available for loading those things in. That way it keeps your hands away from it. You've got a pig. Doesn't look like a pig, does it? But that's what it's called. It's a pig. Should be labeled, shielded, never left unoccupied in transportation. Know what the route is so you know where it should be going. And you should avoid exposing the general public with this. There was a story once of basically old radiation sources here that were decommissioned and I believe sold off without any sort of tracking or whatnot, were sent, I believe, south of the border, ended up being put into vehicles or other types of equipment, which ended up coming north of the border. And the only reason that got caught, that those radioactive sources were actually being reused, was that some of the materials were actually going by Los Alamos, where they had detectors out near the road. They were going off, obviously, to detect if anybody's trying to escape with those kinds of sources. And then they had detected that certain types of materials were actually still being used in general exposure to the public. That's the kind of thing that you want to avoid. And that's why these regulations are put in place. The reason we have laws is because somebody decided to go out and do something that they shouldn't have done. And now everybody gets forbidden for the fun of having to do certain things. Well, it's the same thing here. These regulations are put in place so that people don't have unnecessary exposure to these kinds of things. Room design. Properly shielded rooms are not always available, so sometimes portable shielding is what's necessary. A shielded hospital bed. It's uncomfortable, it's impractical. We'd like to avoid that as much as possible. Nursing floor rooms have added shielding to the door to prevent it from escaping. They're usually at the end of the hall, so nobody goes down there. Not generally on the first floor, usually a larger room. Why? It allows more distance between you and the source. And you have a door interlock to regulate who comes in and out. Obviously, the source preparation, you have applicators, you got catheters, after loading devices to try to help protect the practitioners. Obviously, you have source preparation techniques as well as cleaning applicators to make sure that you catch what may be left over. You can see source preparations here. You see that eye plaque right there. It's being applied, delivering its dose there to the side of the eyeball, which Personally, I have never been a part of. I've read the theory about it, and quite frankly, that's about as close to it as I want to get. Here you've got a picture of a computerized remote afterloader with the transfer tubes attached. Obviously, you want that thing set so that it can be regularly used and predicted. And that way you know where this source should be traveling and for what distance, that kind of thing. How long is the wire to extend for those particular types of channels? There's a lot that goes into that. You might not think about it on the face of it. So what do you do if, say, you have had this stuff applied to you? No bed baths. You minimize the time spent with the patient. You obviously inform housekeeping as to what's going on. Bandages need to be surveyed before disposal because you don't want to throw out a seed that may have gone missing. Same thing with the linens. And the patient should be confined to the bed, which I'm sure is, always easy to do, right? Um, the handling of radioactivity is obviously something that you have to be concerned about. One of the things that you can do to make sure that the source is doing what it should be doing is an autoradiograph, where the exposure of the source darkens a film and the film is scanned to check the dose uniformity, make sure nothing's wrong with it. And a good QA program is crucial for the safe administration of brachytherapy, because you don't want things going wrong with that. Obviously, leak testing, area room, and surveys should be done so you can see how much dose is actually being transmitted, and measuring, after the sources have been removed, make sure you didn't miss anything. Radium leak testing. A radium source can be checked for radon leaks by placing it in a small test tube with some activated carbon or a ball of cotton. After 24 hours, the cotton ball can be counted in a scintillation well counter, and it's leaking if it's above a certain activity. So that's a general discussion there of brachytherapy. You can learn more, obviously, if you want to go here to the key points for chapter 15, discusses a little bit more in general. And of course, there's always the reading to do there in the chapter itself.